Okay, I see that some participants are already in the room. Um, Hello, everyone. Thank you to all attendees for joining us today. My name is Luis Angel Martinez, a current graduate student at Joan Shaw's group at UCSD. And I have the honor to host today's speaker, Professor Andrew Musser, here present. Uh, before getting um, before getting into our speaker's presentation, let me first bring to your attention the existence of this polariton chemistry community Facebook page, where we encourage all researchers working on this field to post their more recent contributions. And also we believe that this will be a good place to start conversations around topics of interest for the community. So feel free to post your most recent papers, open graduate and postdoc positions advertisement, etc. On the other hand, we have set up a YouTube channel where we post the recordings of webinars in case you want to catch up with some of them, in case you miss them. So be sure to subscribe. Finally, as we usually do throughout this webinar series, we encourage participants to ask questions to the speaker anytime during their presentations. In case you have one or more questions to the speaker, press the raise hand button and I will notify the speaker. Okay. With that being said, let's move on to today's presentation. It is my pleasure to introduce Professor Andrew Musser from Cornell University. Andrew originally trained as a physicist with an eye towards solving global problems. Not infrequently accused of being a spy, he spent 2 years working and studying in Russia and tried his hand at organic synthesis at Max Planck Institute in Mainz, Germany, and genetic engineering at the Manchester Interdisciplinary Biocenter in the UK. He chose to make a proper return to science in 2008, enrolling in the Nanoscience Master Program at the Cernik Institute for Advanced Materials under the supervision of Professor Andreas Hermann. Equipped with this understanding of how to design and make such functional materials, Andrew turned to the main task of his PhD, saving the world with green energy. He joined the optoelectronics group at Cavendish Laboratory in Cambridge in UK, under the supervision of one of the pioneers of organic electronics, Professor Sir Richard Friend. Working in the laser lab, he used ultrafast spectroscopy to unravel the mechanism of singlet fission. In a subsequent postdoc within the same group, he began to explore more elaborated spectroscopic methods and sophisticated molecular materials for fission, building up his network of collaborators along the way. By 2016, it was high time for a change of scene, and Andrew moved to the University of Sheffield Department of Physics for a postdoc with Professor David Litsey into exciton-polaritons. Organic materials are often mocked or scorned in this field for being dirty, floppy, or ill-defined, but they offer even more exciting opportunities, ranging from enhanced charge and energy transport to catalysis. Andrew led a study into the effects of polariton formation on singlet fission and related phenomena, leading to the breakthrough finding that this strong coupling results in entirely new and more efficient ways to molecules to emit light. Finally, in summer 2019, Andrew found his natural home as a physical chemist, joining the faculty of the Department of Chemistry and Chemical Biology at Cornell. He now aims to weave together the many strands of his past research, exploring light-matter interactions with complex materials for fundamental study, functional applications, and the pure fun of it. And with that being said, Professor Andrew, please start your presentation. Thank you.
Well, thanks a lot for the introduction, Luis. It's a real honor to be able to participate in this excellent webinar series. I didn't really think back when it started that we'd still be doing it at the end of October, but there you go. So I'm going to be talking to you primarily today about the work we published this year on some interesting spin physics in organic exciton-polaritons microcavities. And towards the end of my talk, I also want to get into some new and unpublished results that we're still piecing together, looking at how we can understand the ultrafast dynamics of polaritons using the standard tools of ultrafast spectroscopy. But before I dive in, Slideshow is not working. That's unfortunate. Before I dive in, I just want to give you the frame of how we look at these things in my group, what our perspective is. So my group is sitting at the intersection between polaritonics, organic photophysics, and ultrafast spectroscopy. And the main aims that we have are to use polaritons as a tool to manipulate organic photophysics, change excited state dynamics, and hopefully create new functional properties for organic materials. But at the same time, we want to take advantage of the rich photophysics that some of the most interesting organic materials have today to help us understand in new detail what is actually going on in the strong coupling regime. So we use both of these to inform the other, and everything is underpinned by our ultrafast spectroscopy techniques, both in my lab and with my collaborators. So as a spectroscopist, I tend to work in stories. We all like to tell stories of what happens in a material as you photoexcite and the energy rattles down to some final state. And our stories usually look something like this. We have a ladder of states of different characters. You have your singlet states, maybe triplets. If it's a singlet fission material, triplet pair states. And implicit in these pictures is usually an idea of static nuclei. So we have these well-defined electronic states with well-defined energies, and we assume within the Born-Oppenheimer approximation that everything is just holding rigid while we deal with conversions between these electronic states. But actually, we know that in a lot of organic materials of interest, that's not really what happens. These organics are floppy and messy and greasy, and they move around all over the place, particularly at room temperature. And actually, these motions have really significant impact on the energies and the dynamics of the electronic states. So we know that these motions can cause potential energy surfaces to shift relative to one another. It can drive couplings between them, force electronic transitions from one state to another. And they allow different potential energy surfaces or different types of electronic states to mix together. So we really have to think about organics, especially for complex phenomena, in a much richer picture where we allow the molecules to move around. We allow this complexity where different types of electronic states can mix together. And oftentimes this mixing, whether it's coupling to vibrations or mixing between different electronic states, is what drives the processes that we're interested in the first place, in this case, singlet fission. And our contention is, even though looking at materials in this framework where we have to deal with this really complex mess of states becomes more challenging on the surface, with the right set of spectroscopic tools, usually application of complementary spectroscopic techniques, we can actually begin to pick apart in exquisite detail all of this mixing and the dynamics as you change from one surface to another. We can look at the nuclear motions, how they correlate with electronic motions, how all of these are coherently coupled to derive electronic dynamics. So that's really our main philosophy, not just in polaritonics, but how we understand and think about organic photophysics in my group. One of the things that this leads us to is the idea that a lot of the most interesting processes in organic photophysics today are driven by some form of coherence or mixing. And this isn't something unique to my group or to the phenomenon of singlet fission. It's starting to pop up more and more all over the different fields of organic photophysics. So various types of vibronic or electronic coherence and this mixing between different electronic states are invoked to explain processes from biological light harvesting to the operation of cutting-edge organic solar cells, singlet fission, even slow processes like thermally activated delayed fluorescence. They're all somehow tied to this ability of dynamic motions of the molecule following photoexcitation to mix together different types of electronic states and induce this kind of coherence. And the term has become so frequently bandied about in so many different types of phenomena that you almost have to wonder, does it actually have any practical meaning? And what I mean by that, I suppose, is while it's an interesting thing to study, one of our ostensible aims as spectroscopists is to understand how materials work, nominally in order to link it to some kind of molecular structure so that we can tell synthetic chemists how to make a better material. That's how we hope to, save the world with better solar cells. So is there some design factor that gives us coherence? And for that matter, is having this kind of coherence or mixing important in order to achieve efficient triplet or charge generation? Is it something that just happens when the energetics of a molecule are already suitable for these processes? And kind of stemming from that question then, I'm not a synthetic chemist, so I'm not going to be making new molecules to try and engineer this coherence. But if we have a lot of materials where we know it's present, can we take advantage of that coherence and take advantage of these mixed electronic states to get new functionality of the materials? Can we harness this complexity to our advantage? And the platform that we use right now to do that is exciton-polaritons. This is getting a bit tiresome. Can I? Okay. It is exciton-polaritons, which I don't think I need to give a definition to this group at this point. So I'll just highlight that we're using exciton-polaritons specifically in Fabry-Perot microcavities, just because they're the simplest form factor for generating strong coupled states. We work with both metallic and dielectric cavities. The main aspects of polaritons that we're interested in from this perspective of changing organic photophysics are that, of course, polaritons offer an amazing platform to sensitively tune the energetic structure of a material. You create new hybrid states with an energy that's governed by the strength of light matter interaction that we can easily tune by changing, say, the concentration of our molecule or altering the energy of the photon through the thickness. So we have this great lever to alter the energy landscape of our materials. And at the same time, of course, the formation of polaritons creates new states which have a new component mixed into the wave function. We have photonic character in addition to whatever complexity is lurking within the organic wave function. And of course, over the last decade, there have been a handful of reports of weird and wonderful effects that you can get in organic materials from strong light matter couplings. So there have been reports of enhanced charge transport or carrier transport, or energy transport, altered chemical reactivity and work function. And many of these effects are actually still not very well understood, but they've inspired a wave of theoretical interest into the broader idea of, can we use these polaritons to rewrite potential energy landscapes and redirect excited state photophysics and give entirely new photo-induced functions? So it's created this idea of microcavity-controlled chemistry. So this is one of the main areas that we're investigating in my group, and one of the main areas I've been trying to work on for the last few years. And the chief platform that I've been using to probe the potential of microcavity-controlled photochemistry is triplet pair photophysics, which I'm familiar with from my PhD and early postdoctoral work. So these are the photophysics of singlet fission and the reverse process of triplet annihilation. So to give you a whirlwind tour, singlet fission is a process unique to organic semiconductors where a photoexcited singlet exciton can share its energy with a nearby ground state chromophore. And this new coupled state can eventually separate into two free low energy triplet excitons. So this has been investigated quite extensively as a way to improve solar cells, because you put in one photon, you get two excited states out. This can help overcome the Shockley-Queisser limit, but also proposes a lot of interesting physical questions. Now, the reason this process can work is because initially the two triplets that are formed are coupled together into what we call a triplet pair state, this 1TT. So this is a spin entangled pair of triplets where the triplets are effectively anti-parallel, so there's no change in spin as you go from the singlet to the triplet manifold. And this allows it to happen very fast and very efficiently as long as the energetics allow. So all of the magic really occurs within this triplet pair state. And like all processes in chemistry, of course, if you can drive it in this direction, in principle, it should be possible to drive it in the reverse. Then it would be triplet-triplet annihilation. And just like singlet fission, it's mediated by this 1TT triplet pair state. But importantly, the work that I've done over the last few years and others has highlighted that this triplet pair state isn't just two triplets sitting next to each other on adjacent molecules. It's much more than that. The fact that they're coupled into a singlet state allows mixing with nearby singlet and charge transfer states. This gives it a significantly different energy than you would expect for just two triplets. And it also receives new and exciting properties like the ability to emit, even though this should be a formally forbidden process. And it becomes surprisingly mobile, almost as rapidly diffusive as singlet excitons. So already in pure singlet fission photophysics, we can see that there's a huge impact from this concept of excited state mixing between states of different character. The main focus of the singlet fission field, I should point out, is this singlet coupled triplet pair state 1TT. And that's because it's the gateway between singlet and triplet manifold, and likewise for triplet-triplet annihilation. But it's important to bear in mind, and this will come up in a lot of the work I show subsequently, that this is only one of the possible triplet pair states. There are 9 different possible configurations of 2 spin-1 particles, only one of them having 0 spin. So these other higher spin TT states, the triplet and quintet manifolds, are going to have different properties. They have very significant impact on the spin evolution within singlet fission, but they don't themselves participate in any of the direct processes between singlet and triplets because they don't have this mixing. So if we want to investigate these triplet pair photophysics within microcavities, we need to have a good system where we know we're going to start with triplets. One of the fruit flies for probing triplet photophysics or triplet pair photophysics in the organics community is photon upconversion. And this is a process where you can photoexcite a low energy sensitizer molecule, undergoes rapid intersystem crossing to form a large pool of triplets. These can transfer to some other host molecule where at sufficient density, 2 triplets will find each other, annihilate, and via a singlet coupled TT state, generate a high energy singlet exciton. So this process is called photon upconversion. It's been very well documented, particularly for this materials combination of a platinum porphyrin and diphenylanthracene. If you put in green photons to excite the PTOEP, you end up getting higher energy photons out, hence photon upconversion. So we can put blend films of this mixture of materials in a polystyrene matrix into a microcavity, and at the right concentrations, we can strong couple to the vibronically structured absorption spectrum of the anthracene. And that's what you see here. So in these color maps that I show, our reflectivity data is the shading, and then we have transfer matrix modeling in symbols and lines to indicate that we definitely know what the states are we're talking about. And it's a bit faint, but you can see that we have slight dips in the reflectivity between these 2 absorption peaks. There's also the start of a dip here around 375 nanometers, and clearly a pronounced dip below the 0,0 absorption peak. So we've got a nice ladder of polariton states, at least a lower, middle, and upper polariton branch due to the vibronically structured anthracene absorption. Nothing particularly surprising here. Anthracene strong coupling is known. The platinum porphyrin absorption is somewhere down here off the scale of the plot at 532 nanometers and doesn't interact with the cavity mode at all. So if we photoexcite these cavities at 355 nanometers, we get the emission spectrum angle integrated, shown in dashed here. Basically, all of the emission comes from the lower polariton branch. If we excite the same cavity at 532 nanometers, we get precisely the same emission spectrum. And all this really tells us is that the photon upconversion photophysics that we know in the neat films or in solutions also apply within the microcavity. And that really just tells us that the excitons between the mirrors are behaving exactly as they would outside of the mirrors. So there wouldn't be much of a story to tell from this alone, but when we use an integrated CCD to look at the dynamics of this emission, we observed quite a surprising difference between the films and the microcavities. So there was substantially longer-lived emission within the microcavity, suggesting that something else is going on in the strong coupling regime to alter these photophysics. And the problem we had here is, while we can tell there's an enhancement, there's no really clear decay profile. This is a classic non-exponential decay that you would be, you're able to fit all sorts of models to, and it would be a bit of a risky proposition to try and draw any strong inferences from this, especially when you consider that the photophysical cascade we're looking at has quite a large number of processes that could conceivably be modified by the presence of the microcavity, even if it's just having enhanced fields. Not least because photon upconversion is a two-particle process, so you have to deal with exciton diffusion and excitation density. And while we corrected for those effects as much as we could experimentally, there's some uncertainty about the exact degree of enhancement that's due purely to polaritonic effects. So we needed a simpler material system to try and pick apart what's really going on here. So we moved on to this DPP dye. This is just a generic organic dye, but we know from external measurements that it has a low yield of intersystem crossing to form triplet states. The triplets are high enough energy that when enough triplets are present in the film, they can annihilate to regenerate an emissive singlet exciton. So the emission dynamics in the DPP dye on its own are dominated by a singlet decay. And then on long time scales, we get some delayed emission that is correlated with annihilation of these long-lived low-density triplet states. If we put this dye within a polymer matrix and sandwich it between two mirrors, we once again form exciton-polaritons, at least strong coupling to the 0,0 absorption peak. And if we photoexcite these microcavities, all of the emission comes from the lower polariton branch. And now if we look at the dynamics, we see the same basic behavior that we found in the photon upconversion blend, an enhancement in the lifetime of the long-lived emission. But interestingly now, because we have a two-stage emission process, we can see that there's really no change whatsoever in the microcavity on early timescales. So this prompt emission timescale is where the film is dominated by the direct singlet emission. And this clearly isn't strongly perturbed by the presence of the microcavity. But polaritons do seem to influence our ability to collect photons due to triplet-triplet annihilation. And we can confirm that if you quench the triplets in the film by introducing the film or microcavity to oxygen, this enhancement disappears. So comparing these two systems, we can see that we appear to get a unique enhancement in the lifetime of emission when triplet-triplet annihilation is present, when emission is coming from that process. And because there's an increase in the lifetime, it shouldn't just be that we're getting more triplet-triplet annihilation events. It really requires that we're capturing emission from a longer-lived state that is formed in the dynamics. And one of the possibilities is, of course, that triplet-triplet annihilation doesn't always generate the 1 TT state that you want that can generate the S1. Most of the combinations of triplets will give you something that cannot emit and cannot convert into a singlet. And these would be long-lived high-spin TT encounter complexes. So we can start to think that maybe we're capturing some of these in a microcavity. But at the end of the day, this system remains a bit too complicated to draw really firm conclusions. The effect is small. This is still a fairly complicated pathway because we rely on exciton diffusion for these triplets to meet each other. There's a dependence on excitation density. So it's not really a clean system.
Professor, sorry.
Yeah.
Sorry to interrupt. We have some questions here in this part.
All right, great. Fire away.
Hello, Andrew. I have
Hi.
a quick question. Can you remind me, when you say the emission comes from the lower polariton in your experiment, so do you ever have experiments where the lower polariton branch never has any overlap with the bare molecular emission, so that you see drastic changes in the emission?
That is a very interesting question. So that would be a really difficult situation to engineer, I think. The easiest way in principle would be to take a molecule that has a huge state shift. So there's kind of a gap between the absorption and emission peaks, and then place your polaritons in that gap. And we haven't done that. Not familiar with any materials with that kind of state shift that would be amenable to strong coupling off the top of my head. Some of our Tips-tetracene microcavities went to large enough detunings that the overlap with the lower polariton and the profile of the steady state emission is minimal. But the problem, of course, is these thin film emission spectra, which I might have on the next slide. They go out, over hundreds of nanometers. So it's not really practical to push the polariton so that there's no overlap with the emission.
But at least the picture you show is always that at short times, at least the photoluminescence is identical for inside and outside the microcavity, and also in terms of the wavelength of the emission, right?
Oh, well, I mean, the wavelength of the emission is different. So the kinetic in these regimes is identical, but the spectral profile is different. And that could be due to the fact that, of course, the polariton peak overlaps with the film emission. And there's
but regardless, like, I should think about the polariton just as an optical filter in this emission in these emission experiments, at least at short times, right?
Yes.
Is that also the way you think about it?
I think so, yeah, that's fair.
Okay.
This highlights an important clarification I should make about our time-resolved photoluminescence. You'll notice we're only looking on nanosecond, microsecond timescales. The ICC that we're using has a time resolution on the order of 2 to 4 nanoseconds. So we're not able to observe anything related to the coherent polariton. When you directly photoexcite a microcavity, you have this coherent light matter coupled state. That exists on the hundreds of femtosecond timescale or shorter. We're not sensitive to that at all. So everything that we observe, we think is mediated by exciton reservoir dynamics. But like Joel said, the signal that we're getting is effectively filtered by the polariton mode.
Thank you very much.
All right.
All right, we have a couple of more questions.
Oh gosh, okay.
Aaron, go ahead.
Hi, Andrew. Thanks a lot for your talk.
Oops.
I have to unmute myself. Okay, can you hear me now?
Yes.
Okay, wonderful. This is a really interesting talk so far, and I just wanted to ask if you could elaborate. You mentioned momentarily there before Joel's question about the excitation density dependence of some of these kinetics, because I would expect as you would illuminate the samples with more light, you would make more triplet pairs, the density would become higher, and perhaps you would see some of these triplet annihilation processes begin to dominate the signal that you measure. Do you guys see anything like that, or what do you see?
Yes, so it's not very easy to do in this film because the intersystem crossing process is sufficiently low yield that before we get a lot of TTA processes, we start to burn the system. But in this photon upconversion blend, the intensity dependence is pretty straightforward to see. So if we ramp up the power, triplet annihilation happens more quickly. And we see in films and microcavities, this kinetic gets shorter. we turn down the power, the kinetic goes out to longer timescales, but is of course weaker. So we know that this intensity dependence comes into bear, but we don't have, between these two, we don't have a system where we could easily ramp up the TTA events without inducing other unfavorable processes to make this dynamic dominant.
Thanks.
Sure.
All right, we have one more question.
Okay.
Professor Wei, go ahead.
Could you elaborate a little bit more about that you said the change that you see there is due to the reservoir mode in the cavity. So does it mean that the dynamics of the reservoir mode, or maybe the population of the reservoir mode, is different from the uncoupled system?
Yes, so I guess that's the crux of what we're getting at in this study, whether reservoir dynamics are affected by strong coupling or not. So we interpret all of this data from the perspective that microcavities are predominantly, I guess, photoexcited microcavities predominantly consist of excited states within the exciton reservoir or within dark modes, with precious little steady state population of actual coherent polaritons. And that I know disagrees with some other pictures, but that's our overall interpretational framework. Within that model, then, these dynamics can only be explained as the intrinsic decay of states within the exciton reservoir. The fact that they're very similar means that the scattering process from the exciton reservoir into the polariton is not hugely efficient, it's not especially fast. So the dynamics of the singlet reservoir states are not meaningfully perturbed. The fact that we see an enhancement on long time scales means that something else is happening to the dark states that don't emit very favorably within the thin film, but whether their population is changed or their ability to emit photons is changed can't be detected from this particular sample, which is why we moved on to the next one. Does that answer your question?
Yeah, thank you.
Sure. All right. Can I move on now, Luis?
Actually, we have one more question.
Okay.
Bin, go ahead.
Hi, Professor. This is Bin Liu from City College in New York.
Hi.
So yeah, my question is, so for the time where the enhancement happens, do you have any comments on this kind of timing? Like, because for your two different systems, there are the time when the enhancement happens might be different, right? So do you have any comments on that, on that time?
Yes. So the two systems I've shown, it just relates to when these triplet annihilation photophysics have a chance to kick in relative to any prompt singlet emissions. So here, arguably, there's some triplet annihilation occurring on early time scales, but it's completely swamped by very strong singlet emissions. So we're only able to see these effects once the S1 states have basically disappeared through radiative decay and intersystem crossing. In the previous case, this time scale is a bit longer. That's because the time scale for these intersystem crossing and triplet energy transfer dynamics to occur means that the photon upconversion dynamics actually take a while to turn on in the film or in the microcavity. So we just have to sample a longer time range. So basically, for both types of sample, the time scale just reflects the intrinsic time scales of the material photophysics, we think, rather than something polaritonic.
I see. Okay, thank you.
Okay, now you can oh, actually, there is one more question.
Ooh, so close. Okay.
Yeah, go ahead, please.
Hi. Sorry, I had to ask this. So here you have shown the enormous in the absolute count?
Sorry?
The PL count shown here is normalized.
Yes,
So whether there was any difference in the absolute count?
There will have been a difference in the absolute counts. Basically, we looked into whether we could reliably report the data in absolute counts. The challenge is, of course, excitation of the microcavity system. The efficiency of excitation is much lower if we use the same laser power because we have relatively low transmission and absorption of these photons. So the absolute comparison, we couldn't find a reliable way to make that a reliable metric, and we decided the cleanest comparison we could make would be based on the timescales of the different components of the decay.
I see. So we won't be you won't be able to make any comments on the efficiency of this or the comparison between the efficiency of this conversion.
That is an excellent point. We think, based on the kinetic profiles, the fact that these should reflect the real intrinsic photophysics going on within the cavity, the fact that we get more states emitting on long time scales should mean that overall the quantum efficiency of emission is enhanced because we have the same combination of radiative and non-radiative decay rates here, but there's additional radiation on long time scales.
Okay. So to make the comparison little bit more reliable, is it a good idea to deposit the material in a cavity that is not tuned with any of the states? So you have the same transmission to the cavity.
I see. So basically to measure the thin film type dynamics on a weakly coupled system effectively, so that we're also exciting through a cavity. There are some challenges with that. In principle, it's something we looked into with our Tips-tetracene system in particular as some additional control measurements. It has potential to work, but then there are other complications. For instance, if the cavity mode doesn't overlap well with the emission, then the emission in the weakly coupled system is suppressed. If the cavity mode doesn't overlap with the emission, then it's likely to strong couple. So there's a difficult balance there.
Okay. Sure. Right. Thank you.
Welcome.
Okay, it seems that there are no more questions, so you can...
I will quickly race on then. So these first two experimental systems had some complexities due to the multi-particle nature of the annihilation dynamics, which is why we moved to Tips-tetracene. This is a molecule near and dear to my heart that has been extensively studied for singlet fission. So by myself, my colleagues, and quite a few other groups around the world. So we think as a field, we have a very good picture of what the photophysics in pure films of tetracene are. And basically, photoexcitation generates through very rapid singlet fission on the picosecond timescale or less, this entangled triplet pair state. On much longer timescales, this will undergo spin evolution to higher spin TT states that eventually, on like microsecond and beyond timescales, dephase to give nominally free triplets. So if we put these pure films of Tips-tetracene in a microcavity, we again get beautiful anti-crossings to all of the vibronic peaks. So we know we have this ladder of polariton states. And if we photoexcite these microcavities, we get only emission from or through the lower polariton branch. But now, when we look at the dynamics, we see a really huge effect at a really distinct time scale. So we have this bimodal behavior on early timescales before 100 nanoseconds. There's not really much going on between the film and microcavity. But after 100 nanoseconds, we get this really dramatic enhancement in the intensity and lifetime of the emission. And this is something that now we're able to sink our teeth into, not least because Tips-tetracene, being a singlet fission material, generates the two triplets needed for triplet annihilation from a single photon. So we lose the pump intensity dependence that we had in the other systems. We don't have to worry about exciton diffusion. So this becomes a clean system that we can start to understand. And the first thing that's evident is that there are two distinct timescales in the microcavity emission, which means two different states must be contributing to the emission that we detect. And our mission then is to try and pick apart this system and open up the black box of the polaritons where all the magic is happening and see what's going on inside. What are these states? And this is an outstanding challenge I'd like to get to towards the end of my talk. For this study, we were able to rely on the fact instead that Tips-tetracene has been so extensively characterized that we can get an excellent idea of all of the photophysical dynamics simply through comparison to literature data. So I'm going to walk you through our comparisons in this slide. This is our film and microcavity emission dynamics. We can see that on early time scales up to about 100 nanoseconds, we have perfect agreement with the delayed singlet emission reported by Hannah Stern in 2017. So this emission occurs on the 1 to 100 nanosecond time scale, despite the fact that singlet fission occurs in less than a picosecond. And that's because these two states remain in a thermal equilibrium. So even though the population predominantly resides in this singlet coupled TT state, there's always a chance of thermal back population FS1 giving rise to delayed emission with the same spectrum as the prompt. So we know that this emission timescale just corresponds to this thermal equilibrium following initial singlet fission. In that same study, we could measure the transient absorption of the films, and we found that this triplet photo-induced absorption signal, which captures the population of any states that have triplet character, so triplet pairs, 1TT, 5TT, free triplets, this transient absorption dynamic doesn't significantly decay over the time scale that the delayed emission decays over 3 orders of magnitude. So what this could tell us is that this loss of delayed emission on a 10 nanosecond time constant is due to a change in the character of the excited state rather than a loss of population. And that's as far as we could go with optical spectroscopy. But it suggests that there's some kind of spin evolution occurring on these timescales. We can get further insight by comparing to Leah Weiss's paper from 2016 using time-resolved EPR. So this is a spin-sensitive technique to look at the spin dynamics on ultra-long timescales in Tips-tetracene crystals. So what Leah found was that on the microsecond timescale, you can detect the unique resonance profile of strongly exchange-coupled 5TT pair states. The rise time of this signal in particular is convolved with the instrument response. Actually, in more recent measurements, this would rise on, I believe it was a 20 nanosecond timescale. But this is consistent with the idea that we had from the optical spectroscopy that spin evolution causes the loss of this delayed emission. Leah's finding shows that that's because the 1TT state is transforming into a 5TT state. On even longer timescales, the time-resolved EPR shows that these quintet pair states decohere or separate to give free triplet signatures. So overall, I hope that you will agree with me that this comparison to literature data strongly suggests that the enhancement we see in our microcavities coincides almost perfectly with the timescales when 5TT states, these high spin triplet pairs, are present in the microcavity. And it seems that all of our enhancement is coming from the regime after the singlet coupled triplet pair state has disappeared. So we can put this finding from literature data on firmer ground by modeling the system with a simple rate model. So what we've done here is describe singlet fission with the simplest, the smallest possible set of states. So we have the bright S1 state that can be photoexcited. This can couple to bright TT states, and this really means the one TT pair, the only one that's able to couple to the singlet manifold. But there also exist many dark triplet pair states, such as the 5TT. There can also be weakly exchange coupled triplet pairs or slightly separated triplet pairs. So there can be interconversion between the bright and dark TT states, but this one can't communicate with S1. Both of these can then also dephase to give free triplets in principle through, say, a hopping process. So ignoring the presence of lower polaritons, we can use this simple model to simultaneously describe all of the published data on Tips-tetracene delayed emission, transient absorption, and time-resolved EPR with a single set of parameters that becomes quite highly constrained. And the key result of that is that the bulk of the population on long time scales after, I don't know, 50 nanoseconds resides in these dark TT states, and that's the orange curve here. So if we now put polaritons into the mix and look at our experimental data, our approach to trying to model these effects is to assume that precisely the same photophysical dynamics occur within the microcavity that occur outside of it, and then we want to see what other changes do we need to incorporate in order to describe our results. What we found is that to capture this long time enhancement, we have to we can only explain this through the dark triplet pair states somehow communicating with the lower polariton. And there are two pathways through which this can happen. Either it can communicate directly through this dark scattering mechanism, K-pol-D, or in principle, the presence of polaritons could drive the reverse dark to bright process to be more efficient. And then basically you can go all the way around from the dark states via S1 into the lower polariton. I'm just showing you the results of our model here for the direct scattering pathway. We considered this K- dark pathway as well, but this would actually reflect a change in the intrinsic spin physics of the material, which would be extremely surprising and also didn't give as good a fit to the experimental result. But you can see we can nicely capture the time scale and magnitude of our enhancement by incorporating a small direct scattering pathway from these dark states to the polariton, though this should be formally forbidden. We can modify the model slightly by changing the strength of this scattering pathway to capture the effects of our detuning dependence as well. So it feels pretty robust as a simple tool or a simple toy model to describe our experimental findings. To probe this further, we more recently looked into the magnetic field dependence of these dynamics, and that's because triplet pair states are an excellent playground for spin physics. And to explain this, I need to give you a very brief overview of the Merrifield triplet pair model. The idea is that the triplet pair states take the form of XX or ZY or ZZ. This corresponds to triplet on molecule 1 and triplet on molecule 2, and its spin quantum number. So the singlet coupled TT state consists of a sum of these three symmetric triplet pair combinations, XX, YY, and ZZ. And this is the only one that couples to the bright S1 state that can be photoexcited. Effectively, this means that each of these XX, YY, ZZ, XY, etc. triplet pair states has some fractional overlap with S1, and at zero applied field, exactly 3 of them can provide gateways between the singlet and triplet pair manifolds. So it turns out when you apply a magnetic field to this system, the way that the triplet pair states mix together changes. You no longer have these simple combinations. You alter the number of these TT states that provide a gateway to S1. So this alters the balance between dark states and delayed emission. So this has been well characterized since the 1970s, and much more recently has been investigated more extensively. Following the work of Chris Bardeen, we incorporate into this model the idea of a hopping from these strongly coupled triplet pair states to weakly coupled or weakly bound TT states, where this initial separation between triplets enables relaxation between the different pair states. And this is required in order to explain spin mixing and spin evolution, like the formation of the quintet reported in the EPR spectroscopy.
Professor, sorry to interrupt.
Yes.
So we have one question from the audience.
Okay.
Matt,
Hi. I have a few questions about the mechanism shown in the previous slide.
Okay.
So you mentioned that technically the transition from TT dark to lower polariton is forbidden, right?
Yes.
So is that why you didn't include a transition from TT dark to S1?
That's correct, yes. So based on all experimental reports of singlet fission so far, there's no evidence that you can go directly from S1 to these dark TT states. You really have to go via the bright singlet coupled TT pair, at least as far as anybody's been able to observe.
Okay, so assuming that the lower polariton does play a role then, would you say that the lower polariton basically gives you an optical means of monitoring or of observing the TT dark?
Yes, that's precisely what I think this system is allowing us to do. That's a good way to summarize it.
Okay, and then so my final question then is, do you think any of this mechanism could play a role in the previous experiments that you showed with the other materials?
Yes. So what we think Tips-tetracene is the cleanest system where we can pick this apart in detail, but we think the physics underlying this model apply exactly the same way to the triplet annihilation systems.
Okay.
Because in triplet annihilation, if you take these two triplets, drive them together, they will form a statistical mixture of TT bright and TT dark states.
Okay, and actually I have one more question. So I'm still surprised that the lower polariton could serve as a channel for the TT dark. I mean, if they have the same symmetry as the S1, because if you, like from previous works, right, the polariton channel, since the triplet annihilation is a local process, then you'd expect the transition from TT dark to lower polariton to be like a 1/n times the rate of TT dark back to S1, right? So yeah. I'd expect this channel to be highly suppressed. Do you know how many molecules the lower polariton is localized over in your experiments?
I don't have any feeling about that at all, I'm afraid. Yeah, I tend to think about this in terms of the numbers that Stefan and Jonathan put in their recent review on organic Bose-Einstein condensation, where they worked out, based on like the density of photonic states and typical delocalization, you would expect basically a factor of around 10 to the 5 for suppressing localized to delocalized polariton processes. So, we're working against quite a difficult barrier. The important thing to bear in mind here is the rates we're talking about are not large. So the intrinsic timescale of this rate is on the order of microseconds. And the reason we're able to see it is because the triplets can live for tens or even hundreds of microseconds in the right circumstances.
Okay, thank you.
So we wanted to look at how we can apply this more sophisticated spin-based model to our microcavities and magnetic field effects. So once again, we parameterized our kinetic model based on this Merrifield picture to thin film results, and we used it to simultaneously describe the dynamics that have been reported in the literature on Tips-tetracene and the steady state magnetic field effects that have been reported by Sam Bayliss in crystals of Tips-tetracene and measured by ourselves in thin films of Tips-tetracene. So our kinetic model, within the limitations of a kinetic model where every process has to be exponential, give an excellent description of all dynamical data at the same time as capturing the magnitude and rough curvature of the magnetic field response in the time integrated form. So we know that we have this highly constrained model that effectively describes all of the interplay between bright and dark triplet pair states, the spin interconversion between them, and the linking to the bright S1 state, which gives rise to the magnetic field signature. When we do the same experiments and apply the same model to our microcavities, we find a distinct reduction in the magnitude of the magnetic field response using the same kinetic scheme, and once again applying all of the same intrinsic photophysical rates from the thin film result. We can simultaneously describe the approximate timescale and magnitude of our dynamic effects and precisely capture the magnitude of our magnetic field response. So with one set of parameters, we can describe microcavities, thin films, and all of the relevant dynamics of the excited states that have been reported. So we think this is a really highly constrained model. And the key point is the only way that we can capture this description of the experimental results is by enabling these two channels. So the direct scattering from the strongly exchange coupled TT and the weakly coupled T ... T states directly to the lower polariton. And this, the presence of these rates, which are not weighted by the singlet overlap integral of the 1 TT state, these are equivalent to the K-pole D that I had in the previous kinetic model. So basically the only way that we can capture the magnetic field response, which is really spin sensitive, is to require a direct scattering process from these dark TT states into the lower polariton. And this touches on one of the questions that Matthew just raised, and it's a little bit troubling. It was particularly at first when we observed it, that this process should be entirely forbidden. The triplet pair state is a multi-exciton state that already should be symmetry forbidden from coupling to a photonic state. And on top of it, it involves high spin states like the quintet, which certainly shouldn't couple to a photon. And this required us to go back to the simple pictures that we draw of polaritons and microcavities and consider whether we need to update our understanding of these states and how they function. So we were inspired in our thinking about microcavities and what the states are, how they behave, by some excellent work from Spano and Herrera looking at explicit incorporation of vibrational modes into the strong coupling regime. So this is one of the many works they've written on the subject, where they calculated what will be the polariton dispersion if, in addition to the exciton absorption that we're used to dealing with, you explicitly include on the same level coupling to ground state and excited state vibrational modes. So applying Spano's two-particle model to the strong coupling regime. What this work showed is that you just by including the presence of one strongly coupled vibrational mode, you go from having a single lower polariton state from the exciton absorption to having this whole manifold of dark vibronic polaritons. So these are different light matter coupled states with varying degrees of photon and exciton and vibrational fraction, most of which, perhaps all of which, are one photon forbidden from the ground electronic state, but can contribute to things like microcavity emission dynamics. My bigger picture view of this work is it highlights when you start to explicitly incorporate the complexity of organic materials, their coupling to the strong electron-phonon coupling that they exhibit, you go from having a simple model of single polariton dispersions to this rich and complex manifold of polaritons, which would presumably have then a significant impact on the dynamics of polaritons following photoexcitation. So in analogy to this work, what we propose is happening in our system is that the strong mixing between electronic states that we know from previous work on singlet fission in this and other systems gives rise to new functionality in the strong coupling regime. Basically, all of the long-lived states in our system have some direct pathway back to S1 through this strong electronic mixing. The singlet coupled TT state we know is mixed with charge transfer and S1 configurations. That's what determines its energy. The weakly exchange coupled 5TT state is already known from the Merrifield model, is directly mixed with 1TT through these different spin-spin eigenstates. And the contention, our hypothesis then is that this pathway of mixing means that when you enter the strong coupling regime and mix photonic character into the S1 wave function, all of the states that mix strongly with S1 also have a pathway to couple to the photon. So even though you end up with very weak photon miscibility, we call it, in these weakly coupled TT states, these dark TT states, that gives you a pathway for them to interact directly with the photon. So through this complex electronic structure of the singlet fission materials governed by excited state mixing and equilibrium between these weakly coupled states and very strongly coupled states seen in EPR, we actually have a pathway to manipulate dynamics and detect the presence of dark electronic states in the strong light matter coupling regime. So our big picture take on this is that this opens up a pathway, since this kind of mixing is widespread in organic materials, to start to investigate and possibly control the fates of many other types of dark states in organic materials by coupling to S1. So we don't only have to focus on how S1 dynamics, the singlet dynamics, are altered by strong coupling. Strong coupling can actually alter the playing field entirely. And I was very pleased in this context, right around the time that this work was accepted, this excellent study came out from the Courtney group in Chem, where they highlighted the same basic premise, that the chemical complexity of molecules, rather than being a foe, can be turned into a friend in the strong coupling regime. And it gives you entirely new potentialities, new opportunities to change the fate of photoexcitations in the strong coupling regime through polaritonic chemistry. And this is something we're carrying forward, I think, with a very solid understanding of the complex film photophysics like we had in Tips-tetracene. It's possible then to pick apart even rather subtle effects from strong light matter coupling. And because we have this complex structure of coupled vibrational and electronic states, there are actually a lot of opportunities out there to change the photophysics of materials in ways that we wouldn't have initially expected from a simple picture of polaritons.
Professor,
yeah.
We have one question here.
Sure.
Hi, actually, I just wanted to follow up on my previous question based on what you just talked about. So in the left side, right, you have a mechanism that shows radiative pumping. So based on your mixing of triplet with singlet states, right, you said the triplets, could become bright. So would you say that the triplets then undergo radiative pumping to lower polariton?
Yes, that is an excellent question. It's something we tried really hard to pick apart in our cavities, looking at, say, a detuning dependence. So in principle, these triplet pair states, the one TT state can emit photons. So radiative pumping is a possibility. We couldn't find any direct evidence of radiative pumping in this system because, of course, the one TT state should emit photons in the same way whether you're in the strong coupling regime or not. So it wouldn't explain the enhancement that we observe. The other TT states shouldn't be able to emit photons. Whether the strong coupling endows them with the ability to undergo radiative pumping to the lower polariton branch is hard to say. As far as we could tell, a vibrationally mediated scattering process or a radiative pumping process would give rise to very similar intensity profiles along the lower polariton branch. What we found, if we look at the intensity distribution along the LPB, is there are certain peaks that are indicative of vibronic resonances. But of course, the vibronic structure of emission, which would give rise to the strongest points along an emission spectrum, are governed by exactly the same vibrations that would be strongly coupled in a vibrational scattering pathway. So from the data we have, we can't actually distinguish whether this pathway or some other as yet unformulated mechanism gives rise to the actual population transfer. But that's one of the questions that we're really interested in going forward.
Okay, thank you.
Sure.
By the way, Professor, it's already past 10, so if you could wrap up within a few minutes, it would be great. Yeah, thank you.
I will take a really quick tour through the second half of my talk then.
Sure.
Basically, knowing that we can do these interesting things to dark electronic states, we really want to push the spectroscopy to understand, well, what is the interplay between bright and dark states? How do we change the dynamics of states within a cavity? And this is a technical challenge, not least because the molecules of interest are sandwiched between mirrors. And the gold standard in organic photophysics to probe these types of dynamics is transient absorption spectroscopy, which has been applied a handful of times to microcavities. And I highlight these papers in particular because they all have a similar interpretational framework, which is namely that you can find lots of signatures in transient absorption of what appear to be polariton fingerprints. They have surprisingly long lifetimes, and this allows us to hopefully pick apart what are the dynamics of polaritons, how do their lifetimes change relative to films. The question is, can we really apply transient absorption straightforwardly to make these assignments? And I'll highlight my interest in this is in exciton-polaritons. A lot of this work follows in parallels the excellent work from Jeff and Wei's groups looking at how you can understand the dynamics of infrared vibropolariton states and how you can really define the spectral signatures that you get on photoexcitation. So the key point I want to highlight from previous polariton transient absorption literature, which comes up in all of the papers I highlighted on the previous slide, is under transient absorption, you can see generally an enhancement in the lifetime of the TA signatures compared to a bare film. So it appears that you have longer lived states in the strong coupling regime. And this is accompanied by these really pronounced derivative-like features that tend to center around the polariton resonances, the lower polariton, the upper polariton, and sometimes also around the peak of the bare exciton. So the typical approach finds that these features don't change significantly in shape, whether you excite the lower polariton, the upper polariton, or intracavity exciton states, which has led to the general interpretation that these features can be attributed to the polaritons themselves with no direct signatures of states in the exciton reservoir. And this leads to a potentially really exciting result that I feel hasn't been talked about enough in the field, that these transient absorption signatures assigned to polaritons are extremely long-lived. They persist for tens of picoseconds, but the photonic lifetime of these states should be on the order of 10 femtoseconds. So there's something very special happening with polaritons if that's what they are. This model kind of implies that all of the states that you photoexcite are polaritons. Coming from the polariton condensation literature, on the other hand, the models tend to assume that almost all of the states present in the cavities are uncoupled exciton states with a precious little population of polaritons at any given time. So the question is, which of these pictures best describes the dynamics? In the bulk polaritons picture, the question is, how can you explain these long-lived features? Why are polaritons so long-lived? In the reservoir picture, we have to deal with how to explain what are these features if they're not polaritons, because they sure look like it. And to cut a long story relatively short, we've done a lot of modeling to suggest that you can describe many of the types of features that people see in microcavity transient absorption experiments through other effects that don't take into account any excited electronic states or excited polaritonic states. So if we consider thermal expansion or bleaching of the ground state, we can see polariton contraction effects, which have been reported for the infrared systems quite a bit. There can be transient changes in the refractive index of the organic layer or the mirrors. All of these can give rise to qualitatively similar spectroscopic features in a transient absorption experiment. And importantly, the magnitude of these features can easily match the magnitude of transient absorption signatures that people measure in these experiments, with really minimal changes to these optical parameters. So we're talking about a thermal expansion on the order of angstroms or less in 100 nanometer film can give rise to these really prominent derivative-like features that look a lot like features that people report in microcavities of the same magnitude. Same with tiny changes in the index of refraction of the organic or mirrors. So all of this is to say that we have to use extreme caution when interpreting the transient absorption dynamics that we find in microcavities. We've tested that by looking at some Bedipi microcavities, looking at the pump wavelength dependence, and we see a lot of the same features that arise whether we generate excited states at high energy excitation or excite subgap where no excited population should be formed at 700 nanometers or even 890 nanometers. So a lot of these features can only be explained by optical effects that have nothing to do with excited polariton population or even exciton reservoir effects. But at least we see there are some other prominent features that must at least relate to the exciton reservoir. We can even see quite long-lived features if we perform the same experiment on an empty cavity containing just polystyrene. So no excited states are generated at all in this case, but you can still get this long-lived transient absorption signature due to the types of optical effects that we've been modeling. So this is all to highlight that polariton spectroscopy is actually quite fraught. Being able to assign these spectral signatures to excited states is really difficult. I should acknowledge a lot of the framework we're using to interpret these results. I know that there's a paper on arXiv from the CUNY group that's looking at similar phenomena, and we seem to be on very similar pages here. So at least we're not on our own in proposing that a lot of these signatures are unfortunately not polaritons. But what we have found is that if we interpret all of the long-lived features as due to a combination of these optical effects and bleaching due to the reservoir, we do find slightly different spectral features on very fast timescales, which are within the coherent lifetime of the polaritons. And this gives us hope that using ultrafast spectroscopy, we're actually able to pick apart the real spectral signatures of polaritons and observe what their intrinsic dynamics are without mediation from reservoir states. Main thing we've done with this so far is push forward to do ultrafast transient absorption microscopy with 10 femtosecond resolution and say 10-ish nanometer spatial localization precision. The key point is we can observe the expansion of the excited state distribution following photoexcitation with 10 femtosecond resolution. We can do this over a range of microcavities, varying the quality factor, so the polariton lifetime. And the headline result is that when we go to a higher quality factor of cavity, we see that this polariton distribution expands faster and it does it for longer time. So we know that this is definitely related to the polariton states because it has a dependence on the photonic lifetime. This expansion, though, dies within the coherent lifetime of the polariton, and we end up with a much smaller population distribution that reflects leftover exciton reservoir states. So we're still picking apart these results, but it appears that when we apply very fast spectroscopy, we can start to see some of the intrinsic properties of polaritons indeed. So we can capture their rapid expansion and how they interplay with exciton reservoir states. So due to the limitation in time, I'm just going to skip to the most important slide where I acknowledge the very large number of people who have helped me in putting together these projects. Key to acknowledge on the dark states Tips-tetracene polariton work is Daniel, who led the experiments, and Jenny, who is my close collaborator in a lot of my triplet pair work. Most of that work was done while I was still at Sheffield and funded by the EPSRC and the Hybrid Polaritonics Network. The microcavities in our transient experiments were made by Kyriakos in David Lidsey's group, analyzed with Rahul's microcavity code by my student Scott. We worked with the synthetic chemists and Akshay's group to perform the ultrafast measurements, and worked with Joel and Luis to do some modeling on the Tips-tetracene system. So thank you very much for your forbearance and interesting questions. If you have any more, I'd be delighted to discuss them.
Okay, thank you very much, Professor, for this very interesting talk. So we have 2 questions from the audience. Jaime, go ahead.
Yes, thank you. Thank you. Can you hear me?
Yes.
Yeah, very good. Thank you. So I was very much intrigued by the last figure that you saw with this fast expansion
Yes.
at early times. So if I understood correctly, so this is something that you attribute to polaritons. So I was wondering, you know, the contraction that you see afterwards, why you don't see just a slower expansion? So what leads to this contraction that you see at later times?
So what we think this captures, and maybe it's even easier to show with the color maps, is we actually have two population distributions that are relevant in this experiment. At time 0, we photoexcite 2 types of states. There's some coherent polaritons that we generate, as well as excitonic states within the reservoir. So our interpretation right now is that the polaritons expand due to rapid transport, due to the photonic character and the curvature of the polariton dispersion. But they have a very limited lifetime governed by the Q factor of our cavities. So when we see this collapse, it's because all of the polariton states have decayed into photons primarily. What's left over are the excitonic states that we generated in the middle at the exact overlap spot with the pump pulse that really haven't moved anywhere at all. So what we're seeing is, oops, wrong direction, in this decay is actually just the disappearance of the polaritons that had moved really far, and what's left behind is the pool of excitons that haven't moved much at all. And if we do these measurements on a film or a half cavity where there are no polaritons at all, we find that the exciton population on these timescales just sits there. It expands very, very slowly indeed.
Okay, yeah, it's clear. Thank you. Thank you very much.
Okay, let's move on to the next question. Professor Wei, you can talk.
Hey, Andrew, very exciting talk. So I have 2 questions. For the thermal expansion that you mentioned in the second part of the talk, I would expect that actually cause a shift of the polariton peak in the same direction, which can be distinguished by the Rabi splitting contraction, that where the lower and upper polariton would move in the opposite direction. Is that what you see? I didn't catch that.
So in the modeling, yes. So that's something I forgot to mention. While all of these proposed phenomena that can happen under photoexcitation give qualitatively polariton-like features, so that they all have the same types of derivative features centered on the polariton peaks, the details of these features are very different, and this allows us to pick them apart. So the expansion gives us an increase of transmission just below the lower polariton peak and a decrease of transmission at the upper polariton peak, and that's due to a shift of the microcavity mode to slightly lower energies or longer wavelengths, whereas the contraction, the upper and lower polariton come together.
Okay, thank you
so
for the
we're working now to pick apart in more detail how all of these effects can add up together to give us the kinds of spectra we see experimentally.
That's right, that's right. Yeah, my second question is related to the first part of your talk, the very last part of explanation that you see. You say the dark triplet state coupled to the cavity through the singlet state. So I think that's a reasonable explanation. My question is that then why the singlet state dynamics was not actually modified at all in your observation?
Yeah, that's a really good question. I think, first of all, if we could look at that system on very fast timescales, we might see some modification in the prompt timescale. But what I suspect is the case is that let's see, maybe I can go back to this model. If we use this reservoir mediated picture, the main modifications to the dynamics come from this kind of this trickling from excitonic states into the lower polariton. And for the singlet state, once you're looking at states that are in the exciton reservoir, this dynamic is actually quite slow and not very efficient. It's coming from this radiative pumping mechanism, which is basically given by the radiative lifetime of the singlets, so quite a slow nanoseconds timescale rate, or the vibronic scattering mechanism, which has various timescales invoked, but has never been shown to be very efficient. So to my knowledge, nobody has observed a system in organics where there's a substantial alteration in the singlet lifetime or the singlet reservoir lifetime due to strong coupling, because that scattering is never particularly fast or efficient in my view.
Okay. Thank you.
Sure.
Okay, so we have one final question, if you are willing to take it.
Absolutely.
Professor Bill?
Hello, Andrew. Can you hear me?
Hi, Bill.
Lovely. Really interesting talk. Thank you very much for that. Actually, my question's about the same slide we're on now, number 21. And this is a question that puzzles me a great deal. So we have two different pictures here. If I look at the reservoir picture and the nice schematic you've got of, different molecules or whatever they might be inside the cavity, if we think about this as being two populations, one population being molecules that are coupled in some way, strongly coupled, forming some kind of polariton mode, and then a second population that are uncoupled, how can I kind of figure out whether one molecule is going to be coupled or not? What is it that determines that the involvement of an individual molecule, or is that just a bad way of thinking about the problem?
Yeah. It's an excellent question. This is the crux of what we're trying to get at, I suppose, how we can study these polaritons themselves and distinguish them from the other states. What allows molecules to host polaritons? I suppose part of the problem is, the idea of a molecule hosting a polariton is kind of ill-defined. There will be n molecules in the cavity that are collectively in a strong coupling regime, but that single polariton state is shared over all of those n molecules. So each of them gets a 1/n fraction of polaritons. So, if you want to kind of project onto single molecule states, at any given time, they have a 1/n chance of hosting a polariton, or they all have this tiny admixture. And the predominant states are then these localized molecular states that make up the bulk population.
Okay, but what's kind of, maybe it's because we're trying to use pictures that don't apply very well, but again, looking at that schematic that you were just referring to, then if we think about each molecule having some kind of relatively low 1/n probability of being involved, then actually maybe we should think about it in that way, that all of them are pink, but only to the extent of 1/n.
Yeah.
Would that be a better way of thinking about it?
I think that might be a good way to picture it, which would make the pink entirely undetectable, which I guess highlights.
Of course, that's absolutely.
Polaritons, they're so hard to see. They make up such a tiny fraction that, in a way, it's surprising we can see all the effects that we do, and understanding how that interaction occurs is quite important. But one of the challenges, which I believe, I forget if it was Luis or Matthew who highlighted, I think it was Matthew who highlighted in his question, is these polaritonic states that delocalized over all of these molecules, whereas the molecular states we're dealing with are explicitly localized, and how to express and understand that interaction between the localized and delocalized states from our spectroscopy is also a major challenge. So yes, these cartoons are perhaps overly simplified, but I guess they're principally to highlight the relative populations of states that are inferred from the two interpretations.
Lovely, thank you very much.
Thank you.
Okay. Thank you very much, Professor. Would you please allow me to share the screen just to make a final announcement?
Absolutely. Okay.
Okay. Thanks, Professor, again for your interesting presentation, and thanks all for your attendance today. As a final announcement, next week we will have Professor Karl Borgerson. Please be sure to register at the link shown here if you are interested to attend. Thanks again to all of you, and thanks, Professor, on behalf of the audience, and see you next time. Thank you. Bye.